in theory, it's recording. So we are only going to review for the exam. So let's start with the one question that you know is coming on the exam, just to make sure everybody's got it. The order of the planets, I think everyone here knows it, but I would be remiss if I didn't do it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So you need to have those in that order. And then you're going to be asked to compare some characteristic. And like I said, it could be number of moons, it could be atmosphere, it could be relative sizes, anything about the planets that we've talked about, the atmospheric pressures, something comparative. So that's going to be your one question you know is coming. Otherwise, what are you prepared for? It didn't go forward like I told it to. There we go. This is, honestly, I went through each section of the chapter, took the things that, come on, guys.
I was wondering.
Nobody tells me. Eli's just sitting back there. Okay. I went through each of the chapters and sections in the textbook and looked at the learning objectives for each section, took out the ones that I did not have as learning objectives for me when I was teaching class, and that's how I came with this list that you will see as soon as Panasonic disappears. So the first thing is knowing about light. Chapter 5, we're going 5 through 12. So chapter 5 is about light. And so you need to remember things like the relationship between wavelength, frequency, and the speed of light. That is, frequency times wavelength equals the speed of light. More importantly,
Is this available?
It will be. It's not at this second, okay. But after class I will make it available. Yeah, it on OneNote. You know how to get there. Yeah. More importantly, you need to know what frequency, wavelength, and speed of light are. So frequency has a symbol F. It's the number of cycles per second, the number of times it repeats. We use hertz as the unit. Hertz just means cycles per second, or inverse seconds. Wavelength is the distance for it to repeat. And then the speed of light is a constant if you're in vacuum. We use C for the speed of light in vacuum. So we use V if it's not in vacuum, C if it's in vacuum. And C is equal to a fixed number that you do not have to have memorized. But the speed of light is exactly 299792458 meters per second. It's defined as exactly that. Now the second one is something that I did not bring up the first time when I should have, and I brought it up at a later date when I was like, oh yeah, I should have talked about this. We have two ways that we talk about light. One is as a wave, wherein frequency times wavelength equals speed of light holds. And one is as a particle, that we treat light like it's a BB, if you will. Except for BBs can come with any energy. You can shoot a BB at any speed you like, for the most part. Whereas with light, it was determined by, first suggested by Planck, and then strongly supported by Einstein, that these particles can only have certain energies, certain frequencies, certain energies for a given frequency. So for a given frequency, you can have 1 times HF is the energy, or 2 times HF, or 3 times HF, where H is the Planck's constant, which you don't have to have memorized, but H is just a constant. So energy comes in discrete units, and so since it comes in discrete units, we call those units photons. Photo for light, on to sound like a particle. So the particle of light is a photon with energy HF. Where I brought this up was when I was talking about the importance of the ozone layer. Why is the ozone layer important? It protects us from UV radiation. Why is UV radiation bad? Because it has a high enough energy, the frequency is high enough, that HF is a high enough energy for it to break bonds. And so if you absorb that UV radiation in your skin, you can break bonds in your skin, you break bonds in your skin, then they can form in unwanted ways, making mutations. All right, the difference between light we see from an object with distance. I'm not sure that I talked about that, but I think I did, and it's very simple. Actually, I'm pretty sure I did. If you have a car and you're right in front of it, its headlights look super bright. If it's far away, they look very dim. What's the difference? The light is spreading out as it travels. So even if there's nothing to absorb the light, obviously there is also what we call interstellar reddening, that you have blue light is scattered away, so that you lose some with distance. But even if all of the light makes it to you, the light is spreading out in a spherical shell. The area of a sphere is 4 pi times radius squared. So if you double the distance away from the light source, the area it's spread out over is 4 times larger, hence the amount of light per unit area is 1/4 as much. So it drops off with 1 over distance squared. So that's the key thing. The light drops off with 1 over distance squared. So if stars are farther away, they're going to look dimmer because of that 1 over distance squared relationship. Yes, Mira, excuse me.
Is this like the topic also where you have the blue shift and the red shift? Or is
no, that's coming up, but this is not it.
Okay.
It causes a little bit of consternation because you have the interstellar reddening and you have a redshift. But the spectral lines don't move with the interstellar reddening, whereas they do with the redshift. Okay, then we have understanding the bands of electromagnetic radiation. That is, you have radio waves. Those are long waves. Radio waves can come through the atmosphere. That's another one of these things here. This bottom one here. So I'm doing the bottom two. Radio waves can come through the atmosphere. So we can have Earth-based telescopes for radio waves, such as the Arecibo telescope in Puerto Rico. Huge, 305 meters in diameter, right? Huge thing. Infrared. Infrared light is absorbed by the atmosphere. Visible light. Visible light comes through again. Hence, we can see the sun, moon, and stars. I believe that God gave us vision in this range so we could see outside to the heavens. That's my belief. Now, why would God want us to see the heavens? I think He wants to appreciate it. That's all what I think. Okay, then going on from visible, you have ultraviolet. That's higher than violet, higher energy or higher frequency. And once again, the atmosphere absorbs ultraviolet radiation. In the ultraviolet, you go to higher ultraviolet and you start calling it X-rays. And you go even higher and you start calling it gamma rays. The difference in gamma rays, X-rays, and ultraviolet is actually the source. We don't care for right now. Okay, so we only have 2 bands that light can get through the atmosphere, visible light and radio light. So for any other kind of observation, you really want to get outside the Earth's atmosphere if you want to have any reasonable amount of light getting to you. And even in those ranges, it's better outside because you don't have the atmosphere interfering. Okay, now we have how the light emitted varies with temperature. Now I put one thing here and not the other. I put the wavelength, the peak wavelength is, and I looked up the number this time because remember in class I said, I think it's 2.9 million, but, and then somebody looked and said, yeah, it's 2.9 million. So here I looked it up and now I have 4 sig figs to the number, which is plenty for us. Nanometers times Kelvin per temperature. What this means is if you have a surface that's hot, and remember I brought in the light, made it hotter, and you saw the color change. If it's hotter, then temperature is going up, and the peak wavelength, that's the wavelength with the strongest emission, is going to be getting shorter and shorter and shorter. Or in other words, the frequency is going higher and higher. It's getting more toward the blue side of the spectrum. So that's this equation. We also have the light emitted, called the luminosity, is equal to a constant, the Stefan-Boltzmann constant, times the surface area times temperature to the fourth. And as I said in class, there is the emissivity there, but for a star, the emissivity is just 1, and so we just don't write it for astronomy. The emissivity is telling us how efficient something is at giving off light. Black objects are very efficient at giving off light. The stars are very efficient also at giving off light. So the luminosity is proportional to temperature to the fourth power, and I pointed that out as well when I had the lamps. You saw that when it got hotter, it got much brighter. Because if you double the temperature, 2 raised to the fourth power is 16. So if you double the temperature, it's going to give off 16 times more light. How do we learn about the composition of gases? By examining spectral lines. I'm just going to tell you instead of asking you. Every different gas, that is every different type of atom, has its own unique set of spectral lines, absorption and emission lines. And on the next slide, I think I'm going to have something about how that occurs. So I'll just talk about it now. The atoms have a nucleus that has protons and neutrons. The protons have positive charge. For a neutral atom, you'll have the same number of electrons orbiting as you have protons in the nucleus. And as we understand atoms today, the electrons can only have specific energies. And so if you have an electron in a higher energy level and there's a lower one available, it can fall down to the lower energy level. And just like dropping my pen, if I drop to the lower energy level, I cut my hand because this is a $100 pen. But if I let it fall and hit, you have the sound that comes off. And that sound is carrying away a lot of the energy that it dropped. Well, we have the same thing with the electron. If the electron drops, the energy difference is going to be carried away by a wave. But instead of a sound wave, it's a light wave. And so that light wave is going to have an energy, remember HF, the energy of a photon, that's exactly equal to the difference in the energy levels for the electrons in the atom. So that's how you get your emission spectra. Absorption spectra are the reverse. An electron in the lower energy state, light comes in. If it has exactly the energy difference between this state and one that's open, the electron can absorb that energy, come up to the higher state. So absorption is exactly the reverse process of the emission. So those are both caused by electrons changing energy level in the atom. Then we have the continuous spectrum. The continuous spectrum is much more complicated, at least to my mind, to try to explain. That is actually what Einstein was explaining with his theory, talking about the energy of a photon. But the continuous spectrum is something is hot and giving off light because it's hot. And it gives off light of all different frequencies instead of just specific frequencies like emission or absorption spectrum. Now, while we're talking about this, one more thing to talk about is, remember we had, I think, a quiz question about how to observe absorption or emission spectra. And so remember, you have a star, you have a cloud of gas, and if you look like this, you'll see continuous. If you look like this, you'll see emission, because you'll have electrons that were excited by the light going through to higher energy levels, and then they fall back down. When they fall back down, they give off light in all directions. If you're looking at this angle, you're not looking at the star, so you don't see the light from the star in the background. You just see the emission. And finally, if you look from this angle, you'll see the absorption spectrum. Because you have the light coming in, being absorbed, and so you see the missing lines where it was absorbed. So you have different angles of viewing, gives you each of the different types of spectra when using astronomy.
Wait, so absorption spectra is like the continuous, but it has like missing lines.
That's right. It's continuous but missing lines.
And then emission is like you're seeing the missing lines.
That's right. It's exactly right. Okay, well, 15 minutes in and we're on slide, what, 2? Maybe 3. We're still in chapter 5. Don't worry. Less time in the later chapters. It says, talk about the structure of atoms. We just did, right? So let's get down to ionization levels. Ionization means that you have taken away or added an electron to an atom. It's ionized if it has a different number of protons than electrons. And usually in astronomy, we will talk about them being positive ions, meaning they're missing electrons. Why? Because in astronomy, in a star, you have high temperatures. High temperatures, that was obvious, right? High temperatures mean things are going fast, so you're going to have high energy collisions between atoms. High energy collisions then will transfer energy to electrons and ionize mechanically. That is, you will basically have a collision and knock the electron off of the atom. So in stars, like our sun, for instance, the atoms, except for in the atmosphere, are all ionized, completely ionized. They have no electrons. So when you say you have a hydrogen atom in the sun, you mean a proton. You say you have a helium atom, you mean 2 protons and 2 neutrons, but still no electrons. Even an iron atom, you have 26 protons, I don't remember how many neutrons, and no electrons. Why? Because the collisions are so energetic that it's knocked them all off. And so you have an electron gas, and you have the positive charges in the star. It's kind of bizarre. You don't have that around here, right? Okay.
Does that make it an isotope?
Isotopes have the same number of protons but a different number of neutrons.
Oh.
So there are different isotopes of many different atoms. Each isotope is going to have virtually the same spectra because the mass of the nucleus makes only a small difference, but it does make a difference, so you can tell if you're careful enough. Anyway, if you ionize an atom, like if you take 1 electron away from a helium, you take 1 electron away from a hydrogen, it's completely ionized. There are no electrons. There is no spectra if you take away all the electrons. A hydrogen atom, if you take away 1 electron and leave 1 electron, it's still going to have a spectrum, but it's going to be a different spectrum. Because when you take away 1 electron, the energy levels are going to shift a little. So you can not only determine what gases you have, but what the ionization states of those gases are by looking at the strength of the absorption or emission lines. Now there is another thing. You can determine the temperature. This is actually how astronomers determine the temperature of a star. They look at the relative strength of absorption and emission lines, because if you're talking about, let's talk about absorption lines. To absorb, you have to have electrons in the right starting state. So if you have hydrogen gas in the ground state, the lowest energy state, it won't absorb visible light. And so you're not going to get any absorption spectra for visible light if you have cold hydrogen gas. But as you warm it up, they start hitting harder, and you start having electrons that get mechanically elevated to the second energy level, the first excited state. And the first excited state will absorb visible light. And so as the temperature starts getting warmer, it starts to absorb visible light. Until you get up to about 8 to 10,000 kelvins, you have maximum absorption of visible light. You go higher than that, and you start elevating the electrons up to the third energy level, and the amount of visible absorption drops again. And so there is a peak temperature for absorption, so that's the way they can determine the temperature by looking at the relative strength of the strengths of absorption lines. Okay.
Yep.
Is there a question? The Doppler shift. This is where we get to the Doppler shift. The Doppler shift, in sound, it's easy, right? Doppler shift. The Doppler shift is a shift to higher frequencies if the sound source is approaching you, or lower frequencies if it's moving away. Same idea for light. Slightly different equation because light doesn't need a medium, sound does. But if something's moving toward you, it's going to be shifted to higher frequencies, and we call that a blue shift. If it's moving away from you, it's shifted to lower frequencies, and we call that a red shift. By looking at how much a spectral line has shifted, we can take the amount of shift divided by the wavelength it has in the laboratory, and that tells us the speed of the object divided by the speed of light. So by measuring how much red shift or blue shift you have, you can directly determine how fast it's moving, toward or away from you. You can't tell how fast it's moving sideways. There is a transverse Doppler effect, but we're not worried about that for this class. So you can't really tell sideways speed, only toward and away from you. Okay, we're on to chapter 6. So, the 3 basic components of modern system for measuring astronomical sources. What do we call a modern system for measuring astronomical sources? A telescope, thank you. So, we're looking for the 3 basic components of a telescope. What do you think those are? Okay, there are 2 lenses for the main components. There's the objective, which is the one that is the first thing that the light passes through or reflects off of, depending on which type of telescope it is. You have the eyepiece, the second one, well, the last one. And then you have whatever you're taking a picture with. Because in astronomy, you're not just looking at it with your eye. That's not very easy to share with somebody. So in the olden days, they took photographs. In the modern day, we use the charged couple device, CCD, same thing your cell phone uses, to take a picture. And the CCD has a lot of advantages. I didn't put here, it was in the things, the objectives from the textbook, but I didn't put it here, the variations between CCD and film. Just suffice to say that CCD has many advantages. And so these days, an astronomer can be sitting in his nice, cozy home in Colorado, and provided he has a fast internet connection, he can be doing, state-of-the-art research in Chile or Hawaii, because it's all just done over the internet. The data is collected by the CCD, transferred to you on your computer, you analyze on your computer, so on. 2 basic types of visible light telescopes. I've alluded to them. What are the 2 basic types? Yes. R and R. Refractor and reflector. Refraction is light bending when it goes from one material to another. Remember we talked about, my example is going on the beach and going to the sand, so it slows down and veers away. That's what a lens is doing, because light goes slower in the lens. And so we can shape a lens to take advantage of light going slower when it goes into the lens, and because of that changing direction, to focus light. Or we can use a mirror. A curved mirror is going to change the direction of light differently depending on where it hits. So either a mirror or a lens can be used to focus light. Clear advantage for mirrors. Mirrors, you only have one surface you have to dry instead of 2. You can support that surface very easily, whereas with a lens, you can't support the surface except for the very edges without blocking some of your light. And even at that, if you support it at the edges, it's going to sag under its own weight. So you have those difficulties. Other difficulties, a lens will absorb light. A mirror, you can make it so you just have a very reflective surface, and that's a minimal problem of absorption. A lens has different focal lengths for different colors. We call that chromatic aberration, the error you get because you have different focal lengths for different colors. A mirror doesn't. There's lots of advantages to mirrors. So virtually all modern research-grade telescopes are reflectors. A lot of the little hobbyist home telescopes will still be refractors, but the series telescopes are reflectors. My nose is itching. I'm sorry if you're wondering why I keep rubbing it there. Okay, this is sight. I wanted to go with size. What's the best place to put a telescope? Higher. So outside of the Earth's atmosphere is the best place, right? Because then you don't have to worry about atmosphere absorbing anything or causing light to shift around, giving us the scintillation or poor seeing. But if you can't go outside the atmosphere, you want to go as high as you can. You want to go somewhere that has stable temperatures. It's actually funny. There is a solar observatory in the middle of, I think it's Big Bear Lake. Why in the middle of the lake? I mean, you have water all around. Is that water going to cause a lot of stuff in the air? Well, what the water does is it makes it so the temperature doesn't change much. Makes it so it's a stable temperature. And so they have a telescope out there. It's a solar observation telescope. They observe during the day because that's when the sun's in the sky. What about size? Because I misread that sight as size. Why is size important for a telescope? Okay, larger means that you have more light coming in. The idea of the light bucket. The area is proportional to the radius squared, and so you double the radius, you quadruple the amount of light that comes in. For research-grade astronomy, you're looking for very faint things, so that's a big deal. The second one, I think you also said, it turns out that you have better resolution. You can see finer details if you have a bigger telescope. So there's no downside to big, as long as you have quality optics. Making a nice mirror is going to be a better quality optic. So bigger is better because you have better resolution and can see finer or can see fainter things. Adaptive optics is the cool technique that is making mirrors that will deform to adjust for the scintillation. So you actually have a computer-controlled system that's looking at how the light from a star is wiggling around, and it adjusts the mirror so it would keep that light all focused in one place. And then you look at something else with this, and you get a much better picture. You can get the resolution like 10 times better. See, details are 1/10 the size by using adaptive optics, which is amazing. So it's one of those advances that you know that couldn't be done without computers. So we've already talked about that. Explain the importance of the Hubble Space Telescope. This is for your friend who says science is, it's not, or astronomy is not science because it doesn't help us. The Hubble Space Telescope, how does it help us? Okay, the Hubble Space Telescope takes pictures of lots of different things in lots of different situations. It takes pictures of planets, stars, galaxies, and helps us to understand more about fundamental physics. And fundamental physics, as a physicist, I feel strongly about this. Fundamental physics, you don't know what the application is when you discover something. But that information is often very useful. Everything we have for technology comes from fundamental physics. One of the things that is actually really cool is a crossover that goes the other way. Two gentlemen, Penzias, and I can't remember the other guy's name. They were actually working for Bell Labs, trying to figure out how to use microwaves for communication. Does anybody use microwaves for communication regularly? That's right. That's what they were trying to do, is figure out ways that they could use microwaves for communication, such as in cell phones. And they discovered that they had this noise that was just coming from everywhere. And they're like, what are we going to do with this noise coming from everywhere? They tried to find the source. At first they thought maybe it was pigeons, because there were pigeons that actually, no, the first one was they thought maybe it was because their telescope was too warm. Because if you're dealing with microwaves, something that is at room temperature is actually giving off some microwaves. And so they thought that was it. So they put a cold thumb on there, cool things down, didn't change it. There were pigeons living in their microwave telescope because it's a big thing. And so they went in there and they cleaned out all the pigeon poop and kept the pigeons out. Didn't make any difference. And so somebody is studying up, and he read a paper that had posited that in the early days of the universe, that the universe was giving off all of this radiation, the early days being, we'll learn about that later, the time of recombination. And that radiation, from far distant places should still be passing through us today. And that radiation, because of the expansion of the universe, should have shifted from being very short wavelengths into being very long wavelengths. And lo and behold, they discovered that what they were seeing as a noise that they couldn't get rid of is now what we recognize to be still the signals coming from the Big Bang. So that's something that actually is reversed. They were working on communications, and they found something about astronomy. Yes, sir.
I just wanted to see if I followed this. So you're saying that the Earth has its own particular sound through the wavelength?
Did you say sound?
Yeah, because of what you were talking about.
Well, it's electromagnetic wave, which is a fundamentally different type of wave than sound.
But it's still like connected to the Earth, so it's sort of like you see where I'm going?
Well, what I was just talking about was, and this is something we'll come to in the last chapters of this semester, but the theory, the Big Bang Theory, in a nutshell, the Big Bang Theory was a name that was produced in jest saying, how in the world did the scientists think that this whole thing started with just some random Big Bang? And scientists said, oh, yeah. Well, in the Big Bang Theory, you have the universe a very hot place. The whole universe was in a hot dense. Right, you guys know that song, right? Big Bang Theory theme song? Yeah? Wow. Okay, anyway. So as the universe expanded, as gases expand, they cool. And so the temperature drops until you get to a temperature that's low enough for electrons to combine with protons to make hydrogen atoms. At that point, the universe becomes transparent and light starts passing through the universe. And that light is passing in all directions from all points in the universe. And so no matter where you are, there should be light from a point that's as far away in light years as the age of the universe coming to you from all directions. And so that is what the cosmic microwave background radiation is. It's the radiation from that recombination time where the universe became transparent and then the light just continued to travel. I still don't know exactly what you were talking about, so I just clarified what I was talking about.
I think I follow what you're talking about.
Okay. On to chapter 7. Introduction to the solar system. First we had to talk about things for observing, and now what do we observe? Well, in the solar system, as we talked about, we have the planets, but what else do we have besides planets? Asteroids. Moons. Did you say comets?
Yeah.
Okay, comets.
Stars.
Not in the solar system.
Oh, solar system.
We have one star,
We
the
have
sun.
one star. Sorry, I missed solar system piece.
What else do we have? Now, she said comets. Where do comets come from? Yeah, Kuiper Belt and Oort cloud. So we have these icy worlds out there, the Kuiper Belt Oort cloud objects. Then we have the planets, which have the Jovian planets and the terrestrial planets. We have the asteroids, which are much like terrestrial objects in that they're rocks. And we learned that there's 3 types of them, right? The C type, the S type, and the metallic. Moons. Moons could be like comets, like Pluto. Moons could be like asteroids. Or moons could be like planets. Right? There's some fundamental differences in the moons we have. But those are the kinds of things we have in the solar system. Locations, we already talked about the Kuiper Belt. That's in the plane of rotation of the galaxy. Of the, let's say, solar system. And then we have the Oort cloud, which is the farther out spherical shell. I just talked about those Monday. Coming inside, we have the planets are all orbiting in roughly the same pattern, or same plane. And then we have the moons orbiting mostly in the same plane as well. Not all, clearly. Okay, characteristics of giant planets. Gassy, right? with a big rock in the center. Terrestrial planets, just big rocks. Small bodies and so on. Well, I've talked about those enough. Temperature. This one's dumb. What difference does temperature make to the planet's surface? Well, if the temperature is hot, then the surface is probably going to be, well, obviously if the surface is hot, it's not likely to have liquid water, right? Hot surface won't have liquid water. It clearly won't have ice. It's probably going to be a dry surface. If you have a cold surface, it can have lots of ice. It would have frozen volatiles. The atmosphere is going to probably be thicker in a cold planet than a hot planet. Hot planet, molecules move faster. You're going to have more moving away, bigger chance of losing them. Cold, they just sit around. So temperature makes a big difference to the planet's surface, also to storms on the surface. Geological activity. On Earth, what kind of geological activity do we see? Okay, we have signs of the plates moving. Plates moving pretty much covers everything. Because the plates move causes volcanoes where we have subduction, sliding of a ocean plate underneath the continental plate. It causes stresses in the rocks, which causes cracks in the rock, which we call faults. And when we have slipping on those cracks, we have earthquakes. We have the Hawaiian island chain that's a single hot spot, a place where hot magma comes up through a channel in the mantle and punches through and makes an island. But then because of plate tectonics, the island moves and you punch up another place. It moves, you punch up another place. And so you have a chain of islands stretching from the recent Hawaii, I think all the way down to the area of New Zealand, is all one long island chain coming from one hot spot. As you go down, they're much older, much more worn down, mostly below the ocean level as you go farther away from the current Hawaiian Islands. So all of those are signs of geologic activity on Earth, and they all are tied in with the motion of the plates, the plate tectonics. Make sure you remember the different layers in the Earth: the crust, the mantle, the molten core, and the solid core. Solid core, super high temperature and pressure, so high pressure that it makes it frozen. Molten core, hot just like the solid core, but not quite as high a pressure, so it's still liquid. The molten core makes the Earth's magnetosphere, its magnetic field. We have to have three things to make a magnetic field. You need to have you need to have conducting material that's swirling around in a circle. It has convection. You have to have those three things. Why is this important? Because we use our comparative planetology to take what we understand from Earth and then look at other planets to try to understand them better.
I have a question.
Yeah.
What's the source of the gas and ice giants magnetic field?
Okay, it depends on which one you're talking about. If you're talking about the gas giants, it's liquid metallic hydrogen that's swirling around. Well, not in the core in this case. It's actually pretty far out. In both of them, it's pretty far out. So in the ice or in the gas giants, it's liquid metallic hydrogen. The ice giants, we don't think has liquid metallic hydrogen, and so it couldn't be that. They also have, remember, really wacky magnetic fields. The magnetic fields fluctuate much more than they do on Earth. They don't line up with the rotational poles. In fact, they don't even go through the center of the planet. They're off center. And the understanding of the belief is this is because you probably have ice chunks in a briny, salty water. So it's not just water and sodium chloride. It's water, ammonia, methane, stuff like that. But that stuff swirling around, which we call briny water, is what they believe is making magnetic fields for the ice giants. When I get to those questions now, or those statements, I'll pass over them because I discussed it. How do astronomers identify if a surface is young or old geologically? Hey, do calculus. How do astronomers determine if a surface is young or old?
Looking at the craters.
Okay, craters. If it has lots of craters, is that young or old? Probably old. If it has not many craters, young, right? So that kind of makes sense. What makes craters disappear? What makes a surface young?
Plates. No, like for Earth, what is it? You said there's like a shift in plates that kind of balances it just a little bit. I don't know.
Well, the slow surface evolution is the term we're looking for. Slow surface evolution is the effect of water and atmosphere on the surface to change it. And so that slow surface evolution. Now, impacts will also change the surface, but they're going to leave a new crater. So old surfaces have craters on craters on craters, whereas young surfaces might have a few craters. The Earth's surface is a young surface. It has very few craters. Why? Not because the Earth was never hit by anything, but because it has slow surface evolution that is constantly erasing and regenerating the surface. Dating planets. Okay, one way. You go up to the planet and say, hey baby, what you doing tonight? Dating. How do we determine the age of the Earth? Okay, radiometric dating. Make sure you remember the whole half-life thing. I think that was on the previous test, wasn't it? I think it was. I haven't written the test for tomorrow yet. We'll see if it's on this test. But that's one of the primary ways. We find rocks. We find rocks on Earth from Mars. And then we look at those rocks and we say, hey, what isotopes do we have? And we use the radiometric dating techniques to try to determine its age. So that's one way of dating the planets. Another way is by dating the sun. Determining how old the sun is. Now, we haven't gotten anywhere close to talking about how we determine the age of the sun. But the longest or the oldest rocks that have been found on Earth, are not believed to be on Earth, or from Earth, but are dated to like Mars, are about 4.6 to 4.7 billion years old. And the oldest Earth rocks are somewhere in the ballpark of 4.3 billion years old, as far as we can tell. And by our understanding of stellar aging, the sun is probably somewhere just under 5 billion years old. All those numbers come together to give you a pretty conclusive, yeah, it makes sense scientifically to say that the solar system and all of its planets are probably around 5 billion years, maybe a little younger. Chapter 8, the Earth. Yay. Now, we've been talking about the Earth already, right? We've been talking about all the planets, and we use the Earth as a reference. That's why we have the specific part about the Earth. Already talked about this. Well, the theory of plate tectonics, basically you have the crust is broken up into pieces. The lithosphere, if you want to be technical, is the crust and upper mantle. And then those pieces float along the asthenosphere, a layer of kind of malleable rock. It's hot enough and high enough pressure that it deforms and acts like the grease. And then you have convection currents in the mantle that drive the plates moving. So that's a brief description of plate tectonics. Rift zones. What are rift zones?
Like where the new land is formed.
Okay, you have magma coming up, pushing the plates apart. You have those convection currents pushing them apart. So you're forming a new surface on the Earth. You're forming a new crust at rift zones. How do we know these exist? Well, we observe them. We can take measurements of the magnetic fields on one side and magnetic fields on the other. They mirror each other. We can do radiometric dating. They mirror each other, and you have older the farther you are from the rift zone, younger the closer it is. So we have lots of good reasons to believe, yeah, it's rifting, it's doing that. Besides that, we can actually measure the motion. The motion is measured, sure, in centimeters per year, but it's measurable. What's a subduction zone? I've already talked about it. Okay, come together and the more dense ocean plate slides underneath the less dense continental plate. So subduction, under, slides under. So the ocean plates slide under, they're more dense. It's just the type of material they're made of. Relationship between fault zones and mountain building. Fault zones are places where you have cracks in the earth. Mountain building is when you have something like, the subduction here. It causes stress out here in the continental plate. It causes it to fold. And the crumple zones are mountains. Okay. And we've already talked about the types of volcanoes. The ones that we have, like Hawaiian volcano, are caused by a hot spot. The others are caused by subduction, grinding occurring there where subduction is. The grinded rock. The ground rock melts. Melted material floats up, comes out of the surface, volcano. Atmosphere. What's the lowest layer of our atmosphere? The troposphere. What happens in the troposphere? Or troposphere, I don't know. Weather. Yeah, that's where the weather occurs. That's where all this rain has been coming from the troposphere. What's above the troposphere? Stratosphere. And as far as we're concerned here, above the stratosphere, we have like the mesosphere, but then the ionosphere. So I really only care about those, the ionosphere being the third one I care about. The ionosphere is where you have things like meteors and northern lights. Excuse me. Chemical composition of our atmosphere. What's the chemical composition of our atmosphere, roughly speaking? Okay, roughly 80% nitrogen, 20% oxygen. How did we get that? I did not talk about how we got that because I skipped a lot of points, apparently. Our atmosphere is believed to be the third atmosphere. Not the primary, not the secondary, but the tertiary atmosphere. Why? When the planet was formed, what was the most common gas? Should have been, what gas dominates everything in the solar system, in the universe? Hydrogen. Should have been primarily hydrogen and helium gas for the primary atmosphere, which the Earth could not hold on to. So, it's gone. But then we have hot rock, and that hot rock is going to do what we call outgas. It's going to dry out the volatile gases that are trapped in it. And those volatiles that were driven out would have been rich in things like carbon dioxide, I think methane, stuff like that. No longer here. Carbon dioxide largely sequestered in rock in the ocean. The tertiary atmosphere is believed to have come from comet bombardment. Comets are icy objects. They contain lots of volatile things like water. And the water and nitrogen in our atmosphere today are believed to, and the water on the surface of the Earth are believed to have come largely from comets. Now, nitrogen, some of it from outgases as well, don't get me wrong. But this is our tertiary atmosphere. So we have different sources for the atmosphere. The one today is pretty permanent because the Earth has a high enough gravity and a cold enough temperature that we can hold on to oxygen and nitrogen easily. I didn't talk about the difference in weather and climate. Weather, we see the weather change on a day-to-day basis. Climate is a global thing. Weather is a localized thing. Climate is kind of a longer scale thing. You can't take the temperature today and say, that's climate change. But if you take it over a longer time scale and you watch the general patterns, then you can talk about climate change. Okay, so I didn't emphasize that at all. Greenhouse effect, you better know about the greenhouse effect. Where do we have a runaway greenhouse effect? Venus. What's the result? Hot as Hades. Where do we have virtually no greenhouse effect? Mars. They call it the refrigerator effect in our textbook. Result? Cold at night.
And very hot.
It's actually nice on Mars during the day because it's far enough from the sun. Mercury, it has no greenhouse effect, and it's really hot when it's on the side facing the sun because it's close. Really cold when it's not. So greenhouse effect is important to life on Earth. Without it, it would be too cold. We'd freeze. With it, life is good. But with too much, then we become like Venus. Explain the scarcity of impact created. We've already talked about that. Recent impacts on Earth. Is there evidence for recent impacts on Earth? Now, I showed you a video of something that came into Earth, but it didn't impact. Do we have evidence of recent impacts?
The pictures of the one that knocked down all the trees, but they haven't found evidence of that one either.
Yeah, that's right.
Yes, sounded.
I did show you a picture of the car that got hit with the meteor. That's an impact. It's not a major one, but it's an impact. But we do have some major impacts that we have evidence for. The Barringer meteor crater that Clayton and I have been to in Arizona. Nathan's been there too, just for the record. I took him there 4 days before I married his mother. Yeah. It's my idea of romance. I don't know. I'm a nerd. So we have those. Now, what are the dates for those? The Barringer meteor crater is believed to be somewhere around, I think it's about 150,000 years. And furthermore, it's pretty obvious that there hasn't been water running over the Barringer meteor crater. It's out there in the desert. It's well preserved. And so that suggests that there's not been a worldwide flood in the last 150,000 years, if the dating is correct. Which brings up some considerations for a creationist like me. We have the Chicxulub crater down the Yucatan Peninsula. Or how pronounce it for me? You speak close to Spanish. Yeah. I just don't speak the language. I don't know. I don't want to mispronounce. Oh, wait. I should have looked at Leslie.
Wait, what were you saying? I'm sorry.
Yeah.
Because,
Yucatan?
Huh?
Yucatan, is that right?
what are you saying?
He's talking about the peninsula in Mexico.
In Mexico. Yucatan.
Sorry, I'm a visual person. Yucatan.
Yucatan.
Yeah, Yucatan.
Okay, that one. The Chicxulub crater in Yucatan. That is on this list of things. That crater there is believed, now it was only discovered in the last, 30 years or less. It's believed to be the source of a major extinction event. That there was a huge impact there that caused all kinds of debris to go up into the atmosphere. Well, that debris goes in the atmosphere, whoosh, temperatures change because you're not allowing as much radiation in. It's cooler. You have different combinations of gases. So it makes life very hard for many species. So I don't remember the exact percentage. Over 70% of all living species are believed to have died as a result of that impact. So obviously, impacts will affect our lives. If we're around and we have an impact of that magnitude, who's to say that all human lives will go the way of dinosaur lives? Could happen. And so that's this one here, detail how massive impact changed things. We talked about that last class period about the potentially hazardous asteroids, PHAs, that people are constantly tracking. And remember, I showed the graphic of the paths of these asteroids, and you're like, wow, a lot of those cross the Earth's orbit. So there are a lot of things that could potentially hit us. We don't want any of them to hit us. Okay, now we're shifting over to crater worlds, the moon, Mercury. So what have we learned about the moon through manned and robotic lunar exploration? Has man ever set foot on the moon? One small step for mankind, one small step for man, one giant leap for mankind. Yeah, so I certainly believe that it was not done in a Hollywood studio, that they actually, we have sent humans to the moon. We've examined the moon. We have learned about the moon rock. We put retroreflectors on the moon so we can more accurately measure its position. Where did the moon come from? I mentioned in class that there were lots of different ideas, and I gave you the one that is the accepted one. The textbook lists 3 failed hypotheses and the the one that's currently believed. So those are the three failed ones. The fission theory. The fission theory is the theory that the Earth was here, and then it underwent mitosis. It broke in half somehow. That seems to be kind of flawed, right? They say that doesn't make any sense. So then we have the sister theory, that the Earth and the Moon just formed together. I referenced that when I was talking about it. Why? It didn't capture anyone's fancy. So then we move to the capture theory, that the Moon came flying by and the Earth has strong enough gravity and said, hey, hang out with me for a while. That also has some flaws, like the Moon, too similar to the Earth in composition, things like that. So the current theory we have is the giant impact idea. Now, it's a hypothesis. It's not something that we can say, oh yeah, we've tested that one, it's got to be good. But it's better than the others. And that is saying that something that's about the size of Mars, about 1/10 the mass of Earth, hit the Earth at a glancing angle that just caused lots of the Earth's atmosphere to go out into space and then to clump and to form a ball and become the Moon. That's it. By the way, the Moon has a very small core compared to what you would expect. They believe that's because if it was made from material from the crust and mantle of the Earth, it doesn't have the denser materials that are in the core, and thus less for the core. Continuing on then, Mercury. Remember the orbit of Mercury. Very cool, the 3-2 orbital resonance. Why 3-2? Why not, like the Moon, being tidally locked? Because it has an eccentric orbit. Its distance between Mercury and the Sun changes pretty dramatically. And because of that dramatic change, its speed changes dramatically, whereas the rotation rate has to stay constant for conservation of angular momentum. So to maintain a constant rotational rate and a varying orbital rate, it's fallen into that 3-2 resonance, where it does 2 complete orbits in the time it takes to do 3 complete rotations, and 1 day. 1 day every 3 years. Topography and features of Mercury's surface. Do you remember the one feature I talked about in Mercury's surface besides all the craters? Yeah. The scarps that it has, big not canyons, but big bluffs, lobate scarps. And these are believed to be simply the result of Mercury cooling and contracting. Yeah.
But couldn't that happen with Earth as well? And then it cracked and it broke apart, and then the Moon formed. So
Well, a crack, yes. Breaking apart is a whole lot more than a crack, though, because you take a lot of energy to separate the masses. That's where it just fails to make any sense. How do you have them separate? You can crack them; they're still going to hold together by gravity. Okay. Origin and evolution of Mercury. It's the same as all the rest of them, right? Bunch of material coalesced. Now, did it actually form that close to the sun, or did it migrate in? I believe the current theory is that it might have migrated in, that it didn't originally form as close as Mercury is today. Do you have another question?
I was going to say, the cracks in Mercury, couldn't it be just the tectonic?
Yes. Yeah. As far as I know, yes. I don't know that there's any other tectonic activity there, so it's not the likely outcome, but it could be, as far as I know. Chapter 10, we're almost there. Going to chapter 12, Venus and Mars. Why is Venus hard to observe from the Earth? It's actually a very simple question. Atmosphere is too thick. Yeah, we can't see through that. The Russians have sent spacecraft that have gone into it and landed on the surface. So there has been some actual surface observation. Using radio waves in satellites orbiting Venus, we can map out the surface. So we have good understanding of the surface, both from physical landers and from mapping using non-visible wavelengths to look at it. So on Venus, Venus has signs of geologic activity. Venus has a very, very hot surface because of its runaway greenhouse effect. Its atmosphere is what, a little over 96% carbon dioxide. Very thick, 90 times the air pressure as the Earth has. May or may not be on the test, but it is important to know that Venus is the female planet. All but 2 locations on Venus have female names. They're named for female important characters, goddesses, etc. I'm just going to skip over that. Yeah, we clearly talked about that. Let's move on. Talked about that. Greenhouse effect, talked about that. Mars. I spent a lot of time looking at the surface of Mars because it has some really cool features. Cool features like the largest canyon in the solar system, the Mariner Valley, if you want to say it in English. The largest mountain in the solar system, Olympus Mons, Mount Olympus, if you want to say it in English. It also has the face. It's important for historical purposes to talk about the face because some people believe that it might be a sign of intelligence there. That there were some beings that built a face that looked like a humanoid. The scientific conclusion is it was just a random coincidence of the shape of a mountain and sunlight at the same time the picture was taken. But don't forget that in the same region where you have the face, you have things that look for all the world like pyramids in Egypt. And so the true believer is never going to be convinced that that's not signs of a previous civilization on Mars. Most of us don't accept that as truth. We accept that there's no life on Mars and never has been. Scientists are looking for water. We talked about evidence of water. We started with evidence that there might have been water in the past, evidence of frozen water, then we got to evidence of liquid water, and we have pretty solid evidence. We have ice caps. The polar ice caps in the North Pole, you have water ice that's a permanent ice cap. Forms dry ice in the wintertime on top of it, and sometimes you have water ice. So, we know that there's H2O there. And it's just, right now, it's too cold. Why is it too cold to have liquid water? Well, it lost its atmosphere. If it had an atmosphere, it'd be okay. Lost its atmosphere. Why would it lose its atmosphere? Well, one big reason is it's only, it's a much smaller mass than Earth, and so it can't hold gases as well. Maybe we don't understand things well enough. No matter what you do, you can't make atmosphere there. Some people think you should be able to make a permanent atmosphere there. It's a hard call. What's the primary gas of Mars' atmosphere? Carbon dioxide again, just like Venus. How much is it carbon dioxide? Roughly? What?
I just said over 90%.
Yeah, it's some 94, 95% carbon dioxide. So once again, it's very dominated by carbon dioxide. How thick is its atmosphere? To rough numbers, yeah. It's 0.6% the atmospheric pressure of Earth. So it's very thin atmosphere. If it was 100% oxygen, we'd still die, right? Because that's just not enough oxygen for us to live on. You have to look beyond just the percentage of the gas to say how much total is that. And we just couldn't breathe. We'd suffocate. We've already talked about the ice caps, water, life on Mars. If there's water and if there's an energy source, then life as we understand it couldn't be there. The what is it? What's the name of that little bug? Can live in almost any environment.
Oh, the something bear.
Yeah. Yeah, I can't remember its name, but it could live there on Mars without problem. So there could be life there. Okay, chapter 11, next last. The giant planets. We have they're called Jovians as a group, named after Jupiter. We have the gas giants and the ice giants, as Juliet referred to them earlier. They formed outside of the frost line. Outside the frost line, it was cold enough for volatile things to stick together. And so since they could stick together, they could clump up and make bigger and bigger. And so those plants were able to hold on to volatile gases, whereas the ones close to the frost line, Mercury, Venus, Earth, Mars, couldn't hold on to those volatiles. Hence, not nearly as much material for them to grab onto. So these ones grew big because they could hold on to all the material, whereas the ones close to the sun couldn't hold on to everything. The result is these are largely hydrogen. All of them are dominated by hydrogen, based on theory. No one, we've sent a probe that went 200 kilometers into the atmosphere of Jupiter. It's not been to the liquid metallic hydrogen or anything like that. That's all hypothesized. It's hypothesized based on our understanding of what was present in the solar nebula and the conditions for gathering material. So, this is one of those areas where I could be teaching you falsehood, but I'm teaching you the best knowledge we have. If you go inside Jupiter and Saturn, first of all, on the outside, you have the weather patterns, the belt zone weather patterns. You have winds swirling at very high rates of speed. Fastest speeds of any winds on the solar system are on Saturn. All of these planets are orbiting about 10 hours per orbit, or per rotation, I mean. They're rotating really fast for a big guy. That's, less than half the time for the Earth and Mars to do a rotation. The belt zone patterns, remember that the belts are the lower regions, and those are the darker regions. The zones are the higher regions, those are the lighter regions. Saturn has belt zone regions just like Jupiter, but Jupiter's are much more distinct, much easier to see because of slight difference in the surface temperature. These planets are being compressed by gravity. The gravity compressing them makes them hot, and they're still cooling. They're still cooling from formation. So there's more energy going out than coming in. They're undergoing global cooling, if you will. There are rings around all of them. Every single one of these. But Saturn's are very different. What's different about Saturn's rings than, for instance, Uranus and Neptune? Okay? Saturn has a lot more material in its rings. Uranus and Neptune has very little material. Also, the composition. The rings about Jupiter, Uranus, and Neptune are dark, tiny, ground up stuff. The rings around Saturn are bright, icy stuff. Very different composition. Where they come from, two competing theories. Either asteroids that got too close. Well, it wouldn't be an asteroid for Saturn. That would be a comet. Asteroids that came too close and were torn up by gravity, or potentially something that tried to form too close and just couldn't form and was ground up. You have Jupiter and Saturn have liquid metallic hydrogen that make their magnetic fields. Uranus and Neptune, it's the briny saltish water. Internal heat source is just compression. Magnetic fields. They all have magnetic fields. Jupiter and Saturn have extremely strong magnetic fields, very large magnetospheres. Which planet has no magnetic field at all? Venus. Mars has frozen in remnants of magnetic field. Mercury actually has a very, very weak magnetic field. Mars frozen in, at least to the best of my understanding, it doesn't have a current permanent magnetic field, but it used to have a frozen one now. So they believe the core of Mars is frozen, which goes along with its surface being so hard that there's no plate tectonics action currently going on with Mars. The magnet, well, I said I was going to skip this, didn't I? When it came up, because I talked about it with Juliet's question. So let me just move on. Atmospheric composition of the giant planets. Really all you need to know is primarily hydrogen. right? There are different gases there, but I'm not going to ask you a question about the composition there. The winds we've already talked about. Scale and longevity storms. Okay, scale and longevity storms. I wanted to clarify this. I talked about the great spot on, no, that's the great red spot. Okay.
The dark spot?
Is it Uranus or Neptune now? I think it's Neptune. Okay. I looked it up and now I can't remember which planet it's on. How great is that? Anyway, that big blue spot is what I call it. It indeed disappeared, but another one has come to replace it. So evidence that these storms can come and go, that it disappeared in the 90s and then a new storm has come and there's another one like the one that disappeared. So they're not permanent, although the great red spot on Jupiter has been going on for more than 300 years. That is one long hurricane.
Wait,
Oh.
isn't it shrinking? Earth is shrinking.
I don't recall. Okay, last chapter, rings, moons, and Pluto. Name the major moons of each Jovian planet. Let's start with Jupiter. What are the major moons of Jupiter? What's that? Ganymede? Callisto. Okay, so those are the Galilean moons. Those are the major moons of Jupiter. What about Saturn? What about Neptune? And I can't name any from Uranus.
Which one has Miranda? I can't remember which one that's on.
Don't recall that either. I'm a bad teacher, huh? My encyclopedic knowledge is not quite encyclopedic. We've already talked about the ring structure, don't need to go about that. If we look at the surfaces of the Galilean moons, we have Callisto has a very old icy surface, lots of craters. Ganymede shows more signs of plate action on it, younger surface a little. Europa is a much, much younger surface, has lots of signs of ice, plate tectonics action going on. And then we have Io. Io is not like the others. Io is like hell, right? It's worked so hard by gravitational tidal forces that it has all of these sulfur spewing volcanoes on its surface. It is conjectured that Europa could be a great place to have life because under its ice, it's pretty clear it must have water there because of the plate action. And if you have volcanic vents under the water, you'd have source of energy and water. It's conceivable then that life could live there. So that's considered very exciting. I talked about that. Yeah. This is my last slide, I think. 2 theories of planet ring formation. I've talked about most of these things as we gone through. There's one on Enceladus, of course. Not this. Enceladus. The E ring is a very faint wispy ring in Saturn's ring. So it's a region that is mostly empty with just this little water ice stuff. And what scientists have observed by actually flying a probe close to Enceladus and measuring the stuff that's coming out of geysers, it has geysers, active geysers, and it has the same composition from those active geysers as is in that E-ring, and it's in the vicinity there. Scientists believe the E-ring is constantly being replenished by water coming from the geysers of Enceladus. How cool is that? So we didn't talk about, I'm not going to have it on the test, but I just wanted to mention. Eli.
This is just because of the name. But is it named that because it's related to the gods and it was a giant?
All of the names, well, I should say all of the names. Obviously, when you look at, I think it's Saturn has all of the Shakespearean names.
Well, because like
But
that,
many of these are named after gods. So, gods or mythological things associated with the gods. And all planets have to be named after them. Those gods don't have to be Greek gods, or any other. There's not a special country anymore. Yeah. The last thing there would be how do moons affect the rings? The moons affect the rings by either acting as shepherd moons, keeping the ring material in place, or by setting up resonances, clearing out anything from these orbits because it makes things go up and down and hit other stuff. That is it for my review. You totally feel prepared? Yeah, all right. Alex is ready. Everybody go stay with Alex. The test should be similar to the last one in format. The one question that you know is list the plants in order and then the feature about them. You good? You right?
oh, that wasn't a question.
That was just I guess.
Yeah.
All right. Have a great evening. I'll see you tomorrow.